I would like to extend you a warm welcome to this year's PAG workshop of Pacific Biosciences. My name is Jonas Korlach. I'm Chief Scientific Officer at Pacific Biosciences, and it's a pleasure to host and moderate today's event. So you can see we have a very exciting series of presentations. This year we would like to give our users the stage first, and they will tell you and share their experiences on the PacBio system with you. And then at the end, my colleague Michelle Vieira will give you an update on the current product offerings, the wide range of application areas, and also give you a view of our 2020 roadmap. So before we get started, I'd like to make a few introductory remarks. As most of you have heard, Illumina and PacBio have mutually agreed to terminate the acquisition plans. And so what that means for PacBio is that we remain committed and very enthusiastic to support all of you and to execute on our products offerings, on our technology, what we have today and what we will develop going forward that Michelle will highlight. And so we are really excited and remain fully committed to working with you as we have done in the past to bring you all these solutions that you will hear about today. The second thing, if you allow me to make a few introductory comments, of course, with the advent of the new decade, it is tempting to look back and what happened with PacBio over the last 10 years. And so while doing that in preparation for my talk, I found on my computer this slide, which I presented pretty much exactly 10 years ago at a conference. And so you can see here that where we were is we had built these internal in Menlo Park in California, these breadboards, and we're able to make the smart sequencing technology work. So you see zoomer waveguides and 4 colors and so forth. And so at the time, this instrument had a multiplex of 3,000. So you see on the right here, we were able to then on 3,000 zoomer waveguides see the activity of single molecules of DNA polymerase in real time and extract traces, one of which you see there on the bottom. And so smart sequencing was clearly working, and we were busy at that time 10 years ago to work towards the commercial announcement and implementation. And in fact, just 1 month later, in February of 2010, at the AGBT meeting in Florida, we announced the first instrument of third-generation sequencing, the PacBio RS. And so if I was being asked to describe in one sentence all the hard work by a lot of people of what's happened over the past 10 years at PacBio, it was to take this foundation of single molecule real-time reads with random error and scale up the throughput and the read length. And so that's what we've done with regard to instrumentation, the PacBio RS, RS2, then mid-decade, the Sequel system, and more recently last year, the Sequel 2 system. And in addition, the continued improvement, incremental improvement on the sequencing chemistries, on the software. And so with all of that combined, we were able to increase the throughput of the system by a factor of over 10,000 and the average read length by a factor of over 100. And of course, the latest implementation of that on the instrument side is the Sequel 2 system, which we released and started to ship last April. And this has, compared to the Sequel system, an 8-fold higher multiplex factor on the SMRT cell. And so you may ask, well, how has it been going on the Sequel 2 system? So in this graph, I'm showing the average throughput over the global install base, both for Sequel in blue and for the Sequel 2 system in green. And with the version 2 chemistry on the Sequel 2 system, we're now looking at an average of 225 gigabases per SMRT cell of an output over all different types of experiments, which is about a factor of 15 compared to the current output of the Sequel system. The second aspect that's obviously very important is the reliability. And here we've been able to take advantage and leverage the learning that we have made on the Sequel system, implement that on the Sequel 2 system, and you can see that the hard cell failure rate is under 2% for both systems over the past year. So then one of the things that we're very excited about that is really enabled by having now these really, really long reads are HiFi reads. And so longer reads allow for multiple passes of the same molecule. So on the left, you can see in a graph, that's the raw output. And you can see that for this particular application, up to 25 kb insert size, the polymerase is very stable, and you get between 300 and 600 gigabases per SMRT cell. So in many cases, we see over half a terabase of raw data per SMRT cell run, because the read lengths are so long. They range from about 80 to 125 kilobases on average on individual reads. And what that allows you to do is in a rolling circle sequencing mode for inserts that are up to 25 kb in size is have the polymerase go around that circular template multiple times, generate multiple subreads on the forward strand and on the reverse strand of the same DNA molecule, and build an intramolecular consensus by a process we call circular consensus sequencing, or CCS. And the output of that is a highly accurate long read, which we call HiFi read. On the right, you see the summary stats of what you can expect from an individual SMRT Cell 8M run. So depending on the experiment and the insert size, 1 to 4 million of these HiFi reads, about 20 to 40 gigabases of total data of long and accurate reads. And you see this graph shows the quality distribution. So on the x-axis, you see the Phred score, so Q20, Q30, Q40. And on the y-axis is the number of reads that fall into that particular read accuracy. And you see that the average single read accuracy is now around Q30, or 99.9% accurate reads. Now, these are the summary stats. So I was thinking I would like to describe you what this really looks like. And so by just one example. So here's a HiFi read. And so this particular run was from a few months ago with the version 2.0 chemistry on the Sequel II system. And so this particular read is from a piece of DNA that was isolated from an insect. And it's about 20 kilobases long. And from the initial stats, from the number of passes and from the circular consensus sequencing, the predicted accuracy of this particular read was Q33. That's about 1 error in 2,500 bases on average. And so now with the availability of a high quality reference, we can now ask, well, was this estimate accurate? And so we can map the read to the reference. And we find that out of the 19,820 bases, 19,812 were correct. And we had 8 errors, 8 random errors that are here indicated by these red triangles. And that calculates to an accuracy of 99.96%. Or a QV34, so it's right on with the estimate. And so what that means is you can see that there are stretches of thousands of bases that are perfect, that have no error. And what I hope we'll see in this workshop here at PAG, and what we're seeing in the growing number of publications, is that this is a very powerful data type that allows you to get genome assemblies at less coverage, much faster bioinformatics, less data storage, and so forth. So we're going to hear examples today in the areas of de novo assembly, in the area of isoseq, in the area of targeted sequencing and metagenomics, where the HiFi reads can be leveraged and can bring about unique solutions to your research.